Hello everybody, my name is Matti Tahvonen, I'm from Vaadin and I'm hosting a webinar on big data and MapReduce together with Chris Engelbert from Hazelcast. Welcome.
Exactly. Hi.
So we will be doing pretty practical webinar today, so we will have lots of hands-on coding and we will be watching examples from a real server which is running or which is starting a Hazelcast cluster behind the scenes, and then we have some Vaadin UI which is showing our queries to the backend service, and
exactly.
we will visualize them there.
Yeah, we will have
Vaadin.
some busy business logic going on in the backend, doing amazingly important stuff.
Yeah, and but before we get to actual technical exercises, let's do some warm-up questions. What is big data?
Big data is most of the time not what people think.
Exactly.
So a lot of people think, oh, we capture some data and we have to have some big data tools. But big data mostly means you really have to do overnight runs. You have more than a couple of servers standing somewhere in a data center. Google is a good example. Amazon is an amazing example. Amazon is obviously also an amazing example on how perfect an algorithm can be for something, but not for something else. Like books and movies are amazingly good for related articles or related items on Amazon, but if you have a microwave, you don't want to buy another microwave in the next 3 months, I guess. So big data is a new topic, and it's hard to say that in a few words, I guess.
Yeah, but some big enough data that you just cannot handle on one machine, so you
some
have
statistical
to move,
evidence.
Yeah, you have to do something distributed on multiple.
Exactly.
Yeah, multiple machines. We are using only one machine here today, but normally you would split those Hazelcast instances on multiple machines, and then you would.
Yeah,
it's very easy.
Nodes, something like that.
Yeah. And what about MapReduce? How does it fit into this big data thing?
MapReduce was originally invented by Google. We will see that in a couple of minutes in the slides. They introduced it because they had the need to distribute the data. Obviously, the data they collected while scanning all the websites, and this doesn't fit into one computer, so they had to spread out your search, and eventually you get the results back, and you have to show this to the users somehow.
Yeah, so and do it quickly.
Yeah, right. Do it kind of quickly. You don't want to wait minutes for your search result to show up. So this fits in pretty nicely because it perfectly fits the parallel approach you have to go for the big data analysis.
And Hazelcast, as it's kind of a distributed hash map on multiple JVMs, basically, and then you can use MapReduce style programming to get the data from those. Right.
So Hazelcast in itself is a distributed implementation of the Java collection API. So you have maps and lists in a transparent distributed manner, and we have MapReduce API on top, so you can work on the in-memory data and quickly calculate results.
Yeah. So if you learn kind of the MapReduce style thinking, you can use it on Hazelcast and possibly also some other tools like Hadoop, which was kind of the original open source.
Right. The syntax doesn't really match up, but the general idea of MapReduce is still the same.
You have to understand what happens, and this code gets executed on this JVM. And So how did you compare Hadoop to Hazelcast?
So we often get that kind of question at conferences, and normally I say that Hadoop and Hazelcast fit together pretty well. So if you have a huge amount of data, you know that it takes ages to compile or to aggregate. You can use Hadoop in overnight runs and Hazelcast for the more instant streamlined version where you have instant results, you need quick results like fraud detection kind of things.
So Hadoop, usually you will use some kind of disk there to store the data, and on Hazelcast you will pretty much have everything in the memory.
Right.
Yeah. So they are different tools, but
The-
share some parts.
Right. They're different because you have the in-memory and the disk management, but the general idea is pretty much fitting.
Yeah. How about relational databases? Would you still use relational databases to some job or?
Yeah, so this is, I guess, is more like a question for the general NoSQL area.
Yes.
So since I was working for a couple of companies before, what I find is very important. You can't use either or the other.
Yes.
So for transactional data like payment solutions and something, I still would go for relational database. But for game servers and things where it's not that important, if you lose something in the worst case, go for NoSQL and scale out.
Yeah, but you need lots of scalability and
right,
speed.
Exactly.
Yes.
Yeah. The scalability is more important than probably a mistake you can have support engineer working
and
on.
actually you can often use Hazelcast in front of
right. You
SQL
can use it
database.
as a cache. We have a transparent map store where you can load data transparently from the underlying database, which store them in memory and offer them as a cache, and then you can do in-memory computing on top of that.
Yeah. So then your SQL, often made SQL queries are very fast in that way.
Right.
Okay. Maybe we can go through your slides now and then get to the actual practical introduction.
I hope the text is readable. Otherwise, I have a mouse cursor that I can move to certain locations, which is absolutely new technology, I heard. The first slide is more like the general introduction, what distributed computing means. In this case, in terms of Hazelcast. So we have the user on top. He runs, in this case, a Hazelcast client. So we have a client-server architecture if you want to use that. He wants to know something, so he creates a distributed operation, and this is distributed to all the Hazelcast nodes in the cluster. So we split up the operation. Every of the servers has a couple of data partitions plus backups, which is not shown here. So the data are partitioned equally over all the different servers. And the operation is distributed to all nodes. Everybody calculates an intermediate result for his data set. And in the end, the caller will get all the results and will merge them together to the final result.
Yeah.
So this is what a distributed operation in itself looks like. So our topic today actually was big data and MapReduce. So we tried to come up with a couple of slides, hopefully good slides. So as we already talked about, MapReduce is like the black magic from Planet Google. Even though Google now claims they're not using MapReduce anymore. I think they stated it last year or something.
Yeah, I probably heard that as well.
I'm pretty sure the code base is still
pretty similar.
Yeah, pretty much MapReduce because you can't just exchange everything. Yeah. And still the new streaming API they open sourced is still built on top of MapReduce.
Yeah.
So they just streamlined the API a bit. So typical use cases for MapReduce are things, as we talked about, big data, log analysis, data querying, like search results on Google, aggregation and data summing, which is very common for banks, for example. They want to sum up something very quickly. For example, also for fraud detection, very important. Distributed sorting algorithms are pretty interesting. And you have some basic use case like ETL, which is extract data from somewhere, transform them into something else, and then try to load them into a database. So often MapReduce operations are used to transform from one data source to another.
Yeah.
There are a couple of more things like fraud detection is pretty big nowadays. And I think you can come up with a couple of more if you want to. To explain MapReduce in a kind of easy way, it pretty much is 3 steps. You read data from somewhere in Hadoop from disk. In Hazelcast, they are already stored in memory or in an external backend storage like a relational database. You map them inside of the mapper, which means you can either just select them, filter them, or even transform them. We will see that in the word count example, and eventually you reduce all the intermediate results together to your final result. If you look at the full steps, it actually does a bit more.
Okay, now it got complicated.
Well, it's not really complicated. You can do some additional combining, which is some kind of pre-reducing. So instead of sending the same thing over and over again, you collect it up front and then you say, hey, instead of word, free. So you know, I've seen that word already 3 times, which is just a kind of, how to say that? Yeah, it's less network traffic.
Yeah.
In the easy way. Grouping shuffling, Hadoop calls it shuffling. For Hazelcast, it's more like grouping. It means you send all the same data or the same keys to the same reducer because you want to reduce them. In Hadoop, you can implement that step. In Hazelcast, not yet. Well, we're working on that. So at the moment, it uses the internal distribution pattern from Hazelcast itself. Then we have reducing, and collating is something that came up with InfiniSpan. Since the idea of Hadoop is different from InfiniSpan or Hazelcast, in Hadoop everything is written from read from disk and written to disk. So eventually you have somehow a final result. In Hazelcast, data are always in memory. And when you get all the reduced results, you might want to do something like a top list. Yeah. So you want to have the top 5. That means you already have the top 5 per reducer, but then you want to have the real top 5. So for example, 3 reducers, 1 collating step, and then you select the final top 5 from this 15 intermediate results. So this is like a caller-side final step. You don't need to do that, but it has a quite nice options. A general, so in combination with the first distributed operation visualization, this is pretty much how MapReduce works. You have input values like these 3 over here, and those are split up, so the orange parts go to orange, the green parts go to green, the blue parts go to blue. And then we see, okay, in the shuffle phase, they are grouped together from here and from here and from here to be all in the same reducer. So all the colors get collected together and sent to the same reducer instance. So this is now our intermediate result because we already have them, and now you could do something like really reducing, like, okay, orange bars 6, or blue bars, maybe in this example also 6, but maybe 5. And those would be sent to the caller, and then you get your final result. So many orange bars, so many green bars, so many blue bars, something like that. To show a bit pseudocode, how MapReduce actually works in code, in this case, we're looking at the word count frequency. So you have input sentences, input texts, and you want to extract the frequencies of all the words, how often a word does show up. So you get in a key, which in the later example will be just like a file name, and you get the document, which actually is your real text. And then you split up the document into single words, and for every word you say, well, this word I've seen exactly 1 time. So you have a for each loop, and as you see, if you have 20,000 times the same word in the text, this will send a lot of data. So this is where combining comes in. So per word, we have a list of all the numbers, which currently is just 1 all the time, because we always have 1 time the word. So what we do is we sum up the counts, which ends up in exactly the same number as the elements in the list. So you re-emit the word and the actual count in this term before you send it over to the wire. For reducing, it looks pretty much like combining. As I said, combining is nothing more than pre-reducing. You get the word, you get a list of ints again, and this time the ints will be pre-reduced. So since Hazelcast does some streaming approach, we batch up the operations and we send some data chunks over all the time. So the nodes are pretty much working all the time. So it can be that at that point you have a list of 3 integers that says 6, 5, 24, something like that. And you do nothing else than sum them up again. We will see that in the example. I guess then it will be a bit clearer. This is actually for people that really love math. I really never try to understand that. This is copied from Wikipedia, and okay. I guess it's true. If somebody wants to...
If it's in the internet, it's probably true.
Yeah, right. If somebody wants to tell me that something in this formulas are wrong, please go ahead. I'm happy to fix it.
In the high school, I was pretty good at math, but not anymore. I'm a developer now.
I learned in school that as a developer, you have to be good in math. Yeah. It seems like we're not.
Yeah, I think I've forgotten everything.
I think we're going to the real cool side of the talk, right?
So let's get to the practical side.
Absolutely. We're going to work on a bit of existing code, but we still will be implementing it live. So, for example, I have the word count things here, but I totally ignore them for now. So, as we learned, we need a mapper. Oh, well, let's look, where is it? Here we read our document, so we have a lot of data sources to read, exactly 3 file names, and we read the files using a line number reader, and just
load the data to the Hazelcast cluster.
Right. We're preloading the data to the Hazelcast instance when it starts up.
Yeah.
And the file name is actually the key, and the content of the file will be the document in this case.
And in this case, we are running this UI code in a Wildfly application server, and this is just one application scope CDIP in there, which actually kickstarts the Hazelcast cluster. So we have a 3 different JVMs there running as a simulated cluster there.
Right. So as we've seen in the pseudocode, in the pseudocode, we need a mapper. So let's start by that. We know we have documents, or we have a string which is a file name is key, and a string which is a document in content. So let's go for a tokenizer mapper. And I give it a 0 because we already have that class. And this extends mapper. And let's put this in the new line because you insisted so big letters.
Yeah, there are some people who are not using a very good network, and YouTube nicely reduces the bandwidth.
So the MapReduce API in Hazelcast is completely generic. So we are full aware of all the type differences. So this is actually the input key, which we know is the file name. This is the input value, which in our case is the content of the document. And we've seen in the pseudocode we're having the word, which again is a string, and we have a number, which in this case is an integer, because I guess we don't need a long. The texts are not that long. Oh, well, and it was an interface. Glad to have IntelliJ to tell me that. So let's change this. This is file name. This is content, or we call it document. And we have a context, and the context is actually used to write out the final values.
Yeah, so there is where you emit.
Right, where you emit the values to the... Because I'm a good coder, for sure I'm doing a final value called integer 1, and this for sure is integer value of 1. because
That's
I don't.
a beautiful line of Java
Yeah,
code.
absolutely. Because I don't like auto-boxing. So we know we need a string tokenizer. And the string tokenizer wants our document. And as long as our tokenizer has more tokens, this is where I always have to think about, is it tokens or elements? We get the word, and its next token. And there is a bit of a weirdness in the tokenizer, because if you have any kind of punctuation, this will be part of the word for whatever reason. So what we do is we have the Hazelcast service, and this one has an amazingly important method called clean word, which does nothing else than just cut out the word. And then we take our context and say, okay, let's emit this. We have our word and we have our amazing one. So far, so good. This is the token, the mapper. I think this is pretty easy so far. Okay, let's go on. And I think we're not using the combiner yet, so we can show the difference. So let's go for word count reducer. And since we can create multiple reducers, since we have one reducer instance per key, we're not going for a reducer, but for a reducer factory. And this definitely implements, I know that one, reducer factory. And again, our input key key is string. We know that we getting values of type int, and we are reducing to type int. Okay. Now we see we would get the word here. So if you have, well, if you need to have a reducer that is aware of the key it was created for, you could just put it into the reducer, but for a single word count, we don't need that. So we create a new inner class, which is our word count reducer. And this one extends reducer. I hope this is correct this time. And to make it a bit more readable, let's put it down again. And there we go. This is, by the way, wrong. It must be that way, because this is our value. Okay, what we need to do is we want to sum up, so we need some value. Let's call it sum and instantiate it. And what we do is we just sum
each value.
Right. We're just adding the values to the sum. And we're returning the sum, and this is still by default the old API, but we are going for the new one. So, oh, sorry, forget about it. It's a reducer, not the combiner yet. And we have to instantiate it, because this is important. I always forget this in the live demonstrations. So you get a nice null pointer exception. You have no idea why. Let's call this 0 as well, so we don't throw them together. Okay. Now we have our mapper, our reducer. We want to know how to actually retrieve the data from the map and how to fire up the MapReduce job. In Hazelcast, every MapReduce job starts by the job tracker. He's kind of the master of everything. It's a shared resource. You can fire up multiple jobs in the same job tracker, so they have to share the underlying thread pool and kind of things. It's a way of keeping track of your load in the system. So we need the Hazelcast instance, which is the entry point into Hazelcast itself. You were so nice to offer it to me using the service.
There you go.
And then you say, well, okay, give me a job tracker. And we don't have any special configuration, so we're using the default one. Okay, now we have a job tracker. We need our input data, which is an IMAP. So IMAP, if we look at the class file, extends concurrent map. So we're still in the Java environment. We're using a normal standard Java concurrent hash map or concurrent map. But we have a few extensions like asynchronous methods and kind of things on top of that. So we know file name and document, string, and we asked the Hazelcast instance again for the map, and I think this was called articles, right?
You can
Yes.
articles, yes.
It was. So easy. So, by the way, the articles are very, very important.
That looks like... I've been working in a...
Yeah, right. Looks familiar. Everybody read this at least
company
once.
And, yes.
So these are just lorem ipsum tags. So they will definitely a word frequency per word. And okay, now we have the tracker, the map, and we want to combine them somehow. So in theory, it would be enough key value to just say, okay, you can use the Hazelcast map data structure directly, but we don't want it to have the MapReduce API just to work with Hazelcast data structures. So we introduced an adapter interface, which is key value source. It's like an extended iterator. People can implement it for almost everything. Like if they want to, they can read even data from the web or from a disk. So our data structure is also string. We have the source, and we were nice to the people, so we at least have a couple of static methods that offer the option to use data structures from Hazelcast directly. So these are pre-implemented for list set, for list map, multi-map, which is a map of where the value again is a list, and kind of things. And if we want to have a job, we say, okay, we want to have a MapReduce job, and we ask the job tracker to create it by supplying it with a key value source. Okay, now we have a job. We need to configure it. Everybody that ever worked with Hadoop might know that the API now gets kind of funky. You have a configuration class where you have set class names or class parameters or kind of things. From Hazelcast, everything is completely fluent. It's also a completable feature since we're stuck to Java 6. Sadly, it's not a Java completable feature, but it has the same features. It's completely reactive. You can put in values. You can put in listeners. You can also wait on it like on a normal feature.
Do you have some kind of plans to get rid of old Java version support? Or
we would love to, but sadly we still have customers that stuck with Java 6, and I guess probably the same for you guys, right?
Yeah. There
so yeah,
some
you know the pain.
Who are still stuck on Java 6, for example, and we still need to support that with our main
absolutely.
framework.
So you exactly know the pain.
Yeah.
Well, I mean, I don't want to have my bank updating to every new versions, right?
Yeah, me neither.
Okay, so we have a DSL-like configuration API.
Yeah.
So it's a fluent API. You can just put in everything. So we have the Tokenizer mapper 0, and we have a reducer, and we put in our reducer factory, which was this one, and we say, okay, please submit that to the cluster.
Yeah.
That's it. It's really that easy. And you provided me with a nice method to create the Vaadin chart from this value, from this result. So we're just waiting for the result to finish.
Yeah.
But to show it, we could say future, and then you can add an execution callback, which acts as your entry point into the reactive API.
Yeah. But I think in this case, the result will be pretty much instantaneous. We only have 3 documents and 3 different JVMs. So.
Right, exactly. So this is it so far. To make it a bit more obvious with the combining afterwards, let's add here a system out print line, which shows the value that is coming in on the console, because we want to add the combiner afterwards. Okay, so if we start up the amazing piece of server Vaadin's code, Vaadin master, amazing piece of server code that way.
Actually, the server piece is not ours. It's for Red Hat, but
don't tell anybody.
Yeah.
So it's starting up, and it should come up in a second. Wow, my laptop is breathing already.
Now it's starting up this cluster.
Right, it starts up the cluster in the background, so this is not a Vaadin fault. And we have.
But it's so there is a multicast network. It's kind of detects
right.
its
Yeah,
other,
right. It needs to discover the different nodes and
and
from,
that's why it
from
needs
the cluster.
some kind of timeout
Right.
there. Yeah.
Exactly. That is why it needs a moment to start up. And we hit execute, and we see the different results of a nice pie chart with the different words. I think I can't
Yes.
make it bigger. It works. Come on. Another.
Pretty nice distribution.
Right. It's a good text.
Yeah.
So let's make this smaller again. And if we look at the console, we see 1, 1. Let me make this bigger. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1.
Yeah.
Okay. So far, so good or bad? Whatever you want to see. Okay, let's move on. I said you can do pre-reducing to minimize the network traffic. So let's go on with the word count combiner. And even here you have a factory because you have one combiner per key. Just for the simplicity of the API when you implement it. Because it was more important to have a good feeling for the user when he has to implement it than it should be internal. Right, internally. So again, we have our word, we have the first integer, and we want to combine to an integer. And we have again our word count combiner class internally, and this extends combiner. Oops, wrong key. And it combines one integer to integer. And here is actually the method I was looking for, because I want to override one more, not that one, that one. So the first API didn't have first version didn't have the reset method, so you had to reset the internal state in the finalized chunk method. Because I said, we're chunking data to keep the cluster alive and working. So it is very possible that you have more than one chunk per combiner. So we have, let's call it pre-sum this time. We do exactly the same. Yeah. So we sum it up again. Let's call it value again, just to make it more consistent. And we return the pre-sum as a chunk. And the reset method is called after every finalized chunk, so we have to reset the internal state to 0.
Yeah, but now this is happening
on every node, right?
Yeah, before it's sent to the shared data source.
Exactly. Yeah. So this is word. This actually runs alongside the mapper, so it doesn't consume another thread. So every time you emit something, this will immediately post it to one of the combiners if you have defined a combiner. So, and now we see the nice thing of the DSL-like configuration API, because we can just say, hey, I want to add a combiner at this point, and that's it. And we remember we've seen the once all the time, so let's close this for now. And let's start up the cluster again, and the JBoss server, Wildfly. It's not JBoss anymore. Yeah. This is actually the Streamcaster, I guess.
Yeah.
Or the, what is it called? Wildcaster? Wirecast? Wirecast, right? And we fire it up again, and we see the same distribution.
Yeah, but it was much faster now that we have the combiner.
It was not exactly much faster, but if we look at the
case,
values,
yeah.
this exactly was the same mistake I always do. Let me quickly fix this. So we see a lot of zeros because I can't remember my own APIs. Because here, if you don't have anything aggregated at that point, so if this one is 0, you want to return null.
Okay.
Because we cache the combiners to not recreate them all the time.
Yeah.
But when you create a chunk, you just say, please combiners, please give me all your values, and everything that is not null will be sent over. So let's quickly restart that. And we will see that it works.
I think you could start it in debug mode, and this kind of changes could go in.
I don't trust the hot swap. Oracle, did you hear me? I don't trust the hot swap. So let's see.
It's a funny thing that we had a zero turnaround fellow here on Monday. And
okay, there it is again. And if we now look at the values, we see there are a couple of 1s, but so, there's also 5 and a 6. And those are the chunks that were sent over. So if we would look at the word, if we would store the word in the combiner and print it out, we will see that those are different chunks for the same words with different values.
Yeah. So with combiners, you will reduce the communication that is needed between the class.
If you remember to put in a null.
Yeah, especially then.
Right. So far with the word count, do you think we should look at some questions? If something popped up or something?
Yeah, I can check it out quickly if there is some question related to this exactly.
Yeah, if not, we're just going on.
Yeah, we can go on, I think. I think I have it here somewhere. There. I completely forgot my own job. You had one job.
Yeah,
okay,
exactly.
So far we don't have any questions for this, but if you have some questions for these tutorials as we do them, you can raise them and I can ask them directly from.
Absolutely. So let's go on with something more interesting. The text says we have a simple example that finding all the person named James. I think it says James, yes. Okay. A short pre-story. Don't think about the person that shows up. I hope it's not a real American person. Otherwise, I'm feeling sad for him.
Yep, I have seen your previous webinar or talk about this job set.
Right. It was really a coincidence. I just searched for someone named James and he showed up. I was like, oh,
Yeah.
Yeah. So again, we want to have a job tracker, and we need the Hazelcast instance again. Use so nice handshake in what? Give me what I want.
No.
As you said, you had one job. And we want a job tracker again, and we take the same one. It's default, and whoops. And we have a key value source again, which is, I don't know, let's see what the actual reader said. Where is it? Data reader, there you go. No, not that one. Right. Okay, we have a list, exactly that is it. And this list contains persons because we read in some CSV file.
Yeah.
and we stored them inside of Hazelcast as a nice data structure. It's a simple POJO, nothing special.
Yeah,
Contains
and
name, first name.
as it is a list, it's on each Hazelcast instance.
Right.
Yeah.
Right. So again, here we see list contains or extends the standard Java list. So instead of iList, you can always use list from Java as you would expect it from Java at all. But for the key value source, we need the iList.
Yeah.
To separate, because otherwise you would have to do some type checking internally, and we wanted to prevent that. So we have a persons list, and we asked the Hazelcast instance for a get list, and I guess this was called persons. Okay, and then we have person here as well, and we have the source again, and the key value source from list. Persons. Let's put this in a new line again. I guess it was string, right? So for lists, since you don't have a mapping between something and something else, the string or the key for the key value source is always the name of the list. In this term, it's always persons. So because you have to create key value pairs, we had to come up with something.
Yeah. Just choose some random.
Well, it's not very random. It's very predictable. Let's call it that way. And then we actually need, this is already prepared. We have our persons mapper, and we see we have the mapper. Since we already done some mapper, we're now going over to show more of the examples. And you give the mapper the first name for the person you search for. In this case, it will be James, and then you do some filtering. So as I said, you can use it for transforming, but you can also use it for filtering data. So in this case, we filter for persons for people that first name is James, and only in this case we emit to the context. And then we emit an email address of the person and the person itself as a value.
Yeah.
So we get our job, and we know we're starting by string and person, and we ask the tracker for the new job with our key value source, and we configure it again. We have a mapper, and we say, okay, we have a person. What was it? Person mapper?
Person mapper.
There you go. And we submit this one. So this again is a completable future, and it returns a map of email addresses and the person. So this will be a future. Import the map. Oh, it doesn't fit. It says, right, it's a list. Now your screen size kills me. Okay, and for the same email address, in theory, there could be now a number of persons because we don't reduce it. But we wanted to have someone who's called James.
Yeah.
Okay. So we've nearly forgot this. Now we get back a result of string and list person. Let's call it result for now. And we're waiting again for it. And do we have something? Okay, you created a util, I guess, right? There was something.
Yeah.
You wanted to have the person. Result and reset. Wow. So let's see how we get the first result. Iterator. Don't do that at home, please. This is not the appropriate way to get the first result out of something.
Yeah. So we have a pretty complicated result set because it's a map of
I
lists,
think it looks,
and we are getting the first.
I think it looks amazing.
Yeah.
Let's make it visible for everybody to know this is not going to happen at home. And then, let's see, we have utils list in table.
Yes.
And
this is just a helper which kind of puts the list of persons into Vaadin table.
Right. So I think this should work now.
Yes. So the result is always a map of something, and in this case,
right. Beside the fact you're using a collator, because then you have a final operation that is running alongside, and then you get just a single result or a list of something, depending on what the collator creates.
Yeah.
So this was tutorial 1, I guess. Yes. So it's starting up the cluster again. And it sounds like my laptop is going to burn in a second. And, well, to make the joke better from the early version, this is actually what the sad person is called like. And as I said, I hope he's not really living in New Orleans. And I hope it's not his email address. I mean, if everybody, or if anybody wrote it down, try to write him a mail. If he answers, tell him I'm feeling bad.
You are feeling bad.
I'm feeling bad for him.
Okay.
Yes, in Germany we have a nice saying for that. It's a falscher Versprecher. So it's you use the wrong word for a coincidence, but you don't want to. Okay. So far, any question? I guess this was also still pretty clear.
I think this was pretty straightforward. Nothing yet.
Okay. So let's see, what else can we do? What about if we group all people by the state? So we've seen this guy was from New Orleans, so we know a state, we know the US states, and we're just collecting the people, grouping by state, and returning the result. So this time you have a state select, which is a drop-down field, I guess, right?
Yep.
So it's not selecting by state, it's not grouping by state, but you pre-select a state.
Which group?
Right, and
we
right, and we filter people by the state.
Yes.
Okay, let's do that one then. Again, we have our filter, and we again need the Hazelcast instance. We are so good, so we're using default again. This can be, by the way, configured in an XML file, so you can configure the underlying thread pool and the chunk size and kind of thing.
And do you usually have to go there to optimize the queries?
Yeah, it really depends. So for example, if you have pretty big values from the mapper, you might want to have smaller chunk sizes so the values get sent earlier, depending on how long-running your reducing operation is. So if you have a pretty long-running one, you want to, if you have a pretty short-running one, you want to send data quickly or earlier, whatever. And this time we again have the iList because we're looking for people again. Actually, person sounds weird. It should be people. We have the instance. Come on. Oh, not life cycle. And persons. And you know what? I'm going to be the lazy coder.
Yeah.
We're just showing the good practices here, right? Copy and paste coding.
Yeah, that's what everybody does after all.
And we create the job again. I don't need to paste the one.
Yeah. So we will post all these examples and some extras that we don't have time to go through in this webinar afterwards to the same forum thread, so you can check out all the examples and some even bit more complicated ones.
Right. So let's see.
Then you can do copy pasting.
Right. Then you can go for the real source copy pasting.
Yeah.
And we again have a list of person. So we will have one state, and we will have a list of people inside of that state. And let's call it future again. And we have our job, and we have a mapper. This is already prepared again. This is a state-based mapper, so we put in the name of the state. And this has two purposes to show how you can reuse the same mapper. So if you set a state, it will filter for it. If not, it will use the state only for grouping. So you can either put in a state or you can leave it out, and you will get different results from the same mapper. So let's close this one for now. So we have the state-based mapper, and we want to have, well, how to get the value.
Get the selected state. There is a helper for
get.
Yes.
Wow.
So this gets the
state from the field, I guess, right?
Yeah, from the drop-down select.
And we submit that again. Oh, by the way, if we can't make it possible in time, there is actually the submit method where you can set a collator which will run on caller side afterwards. So what I was talking about, you can have some final operation if you want to have that. And let me guess, we need again the util helper method.
Yes.
And I guess we also want to have, well, let's see. So we have a list then of person. Let's call it people. Yeah. And we have our future. Waiting for the result, and we want to get the state again, right?
Yep.
Because we group by state. And then we can use this amazing helper function again.
And put the people there. I think that's it.
No, this not. It's actually this one.
Yeah.
And remove this one. That's what copy-paste coding is about, right? Removing the wrong stuff that... Oh, I think it's still running. Do you think redeploy works?
I think it works as well.
You are the JBoss master. Sorry, Wildfly. I can't get over it.
I'm trusting the debug mode and Wildfly.
You're not a copy-paste coder, I hope. So, did it work? Oh, we have another problem now. Let me quickly go out the presentation mode and say this should be localhost 8080,
okay,
I guess.
So it didn't open.
Yeah, it doesn't you see? Redeploy doesn't work.
Or it might be actually starting up the cluster again. Even though it redeployed, it started the cluster, stopped the cluster and restarted it again.
Yeah. So this was tutorial 2. And we have North Carolina, so I'm personally a fan
Where was the James?
I'm actually a fan of California. So, you see, we just got people that live in California, San Jose, Los Angeles. So all the nice cities around the Bay Area. For example, Berkeley. Berkeley is pretty nice. We were there in the holidays. Okay. This time we're going to stop it up. How far we are with our time?
We have actually spent already 50 minutes, so...
50 minutes? Okay, so maybe let's do one
more
tutorial,
and then...
Yeah, maybe something. This is not directly MapReduce. So Hazelcast has an aggregation API, which is built on top of MapReduce. That means you can... you can build all the aggregations with MapReduce, but for standard operations like averaging data or summing up or something like min-max operations, we created a basic API that speeds up the purpose of calculating on those data. We are going to have the Hazelcast instance again. This works a bit different from the normal MapReduce API, since I said this is this is hidden from the user, so it is way easier to actually use it. We have a map for people and their salaries. So we have salary year, which is just another POJO. To store any kind of data into Hazelcast, it just needs to be serializable in some kind, either using Java serializable, using our own serializer interface, using any kind of external library. And as long as the user can tell Hazelcast how to serialize something, we're fine with that. And we're doing the transparent distribution for it. So we have our maps of people and salaries. As we already know, we have a key value source. This is still true for, this is still not true. Because we have a supplier in this case. So the supplier is the, not this supplier, this supplier. The supplier is the adapter for the aggregation API. It does filtering for you. It is put into an internal mapper and will work on the filtering, on the selection of elements, and it also can transform data for you. So in this case, we have our person's name, we have the input salary as a POJO, and what we want to have is the pure value of the salary per year. So we have our supplier, and we have supplier all because we don't want to filter, we want to have all people. But what we want to do is we just want to have the annual salary. So for people that don't know this API yet, this is actually a method handle from Java 8, which is pretty straightforward, a method call that you can pass in, something like that. It's an implicit lambda if you want to. And then you say, okay, I have a map and I want to aggregate, and you pass in the supplier and you choose the aggregation from the predefined aggregations you want to do, and in this case we want to do an integer sum, and introduce it, and this is the sum. And if we write this out, new header salary sum, and some Vaadin thing.
Org Vaadin.
Oh, there you go.
Yeah.
Right. So let's restart server. So as I said, you can implement this with MapReduce. I guess it's clear. We did the summing already. It's clear how you could do that by you map over the salaries, and you inside of the mapper you extract the salary, annual salary, and emit this to the context, and would do the sum as we did before. But as you see, this is just 2 lines of code instead of all the different classes, which are hidden from the user and built in internally. So if we look at the 7th one, we see that all people together get a salary that I would love to have.
Yeah, but so does this have some kind of performance drawbacks now?
Drawback? No, it doesn't. We might quickly, I'm not sure if it works, can quickly look into the implementation, and we see if I look at, let's stop this server before my MacBook actually burns down. As you see, the aggregate function is implemented as a job tracker, and the job tracker is passed to the aggregate, and that is actually just a MapReduce operation.
Yeah,
it's just hidden from the user to make it nice.
Yeah, so it's kind of
right.
up.
It's actually the exact same operation, just in an easier fashion for the user to do.
Yeah, that's definitely for me.
Good, glad to hear that. At least one user. Okay.
Yeah. I think we have done enough of those tutorials. I will paste this link to this example project where we have all those. And also we went straight to the tutorial 7, so we skipped 4.
I think we skipped 3, 4, 5, 6, something like that.
Yeah, so you can also check out those afterwards.
Right.
And
we will upload everything.
Yes. Before we quit, we could just check a couple of questions that we had beforehand.
Okay.
Actually, one question was about is Hazelcast a replacement for Hadoop, but I think we already answered that.
I think we talked about this earlier. So I think they play pretty well together. Since the purpose, even if it both is MapReduce, is still different. You want to have an instant result compared to long-running, real big data approach. Yeah.
Another question, I'm not sure if you are the right expert, because this is more for maybe for the Hadoop or Aerospike, because someone is, or it's Bruno, who is asking, why does this kind of system seem to work better with Unix systems than on Windows?
Wow. I guess this is a general, I guess he refers to this as Hazelcast. I don't know. I think this is more like a general Java problem. I don't want to insult anything working for Microsoft, but it seems like the memory management on Linux works better with Java.
Okay.
No idea why. Maybe the guys at Microsoft could look into that, since they are now heavily working on the Java side as well.
Yeah. So you think it's kind of a JVM compatibility? So JVM is just more performant on some...
Yeah, at least it feels like, not only for Hazelcast, but for almost all Java application, it feels like Linux is the better approach.
Yeah.
But since Microsoft is heavily investing into Azure and Java on Azure, I guess this might change in the future, in the near future.
Then Sangeeta is asking if or how Vaadin components like tables and charts can handle display of big data. Well,
I guess this is more like your question.
Yeah, well, it's kind of my question, but if there is a big data, you are pretty much never showing the actual whole data on your UI.
I think you support
it's all
paging,
about
right?
we have paging. Yeah, you can page it, and we actually the current official version of the data table that we used actually in here, that supports something like 500,000 rows.
JavaScript.
On the UI side. But then it kind of fakes in the browser that those things are loaded from the server side. So you could do something like it's lazily loading it from the backend.
Okay, so it doesn't show everything at once.
No, because otherwise
nice.
you couldn't. There would be not possible to send all that data through the wire to the client.
So it doesn't have the data cached on client side, it reloads
it's on the server.
Okay.
And then you could make some kind of lazy hooking into your big data, but, well, who does want to scroll that many roads? The next version of Grid, actually, it supports even more than 500,000 rows.
Yeah, and on Hazelcast side, we also have paging support. So I guess this could be combined, for example. Every time you reload something, you fire up the next page.
Yeah, exactly.
Inside of the system.
So it's possible to make it lazy loading so that you don't need to pull all that stuff there to the client. And it's still easy and responsive. And pretty easy because you can just use the Java APIs and connect it all together. So yes, they do support, but be sane. The chart that we actually had there, that doesn't have any kind of, and it couldn't probably have any kind of lazy loading. But on the other hand, we just learned MapReduce algorithm so that you can make pretty nice analysis, which is distributed on those nodes, and then you can get some kind of
streamlined result straight to the client. Exactly.
Yeah. So nobody wants to have thousands of slots in the pie charts. What are these?
Maybe he does.
Yeah,
he asked for it.
I think we already have too many slices in our pie.
I like the pie.
Yeah.
Any more questions?
There are a couple of more questions, but I think we want to wrap it up already. We have spent more than 1 hour already, so this is the typical webinar. We have too much stuff that we want to discuss, but we can answer some of these questions on the forum later. And if you have any other questions that relate to this topic, feel free to still add them to the forum, and we can check them out later. And we will give you the answers during the next
Feel free
week.
to ask anything you want to.
Yes. And
but I don't give any marriage tips.
Okay, me neither.
Okay.
Thank you. Bye.
Bye-bye.